Hello. In the second part of the ESD demonstration videos, I'm going to show you how you can work with gridded data. So basically we have to activate the ESD package, and then we use retrieve to read the data from a netCDF file, like that. Also, we want to just, at this point, just work with the annual mean temperature rather than the monthly data, so it takes a little while to go through and estimate all of those. It's a big file, but that will also reduce the size of the data, so it will take a little while to compute the annual mean data. And it's on a laptop, but it will soon be finished. The next thing I want to do is then to show a map of the so basically this is a mean temperature here map. I can instead I can write function equals SD, the singular standard deviation, like that, and run that, and then we get the standard deviation here instead. So you can see the strongest variations are up near the ice edge. We can have a trend as well. So if we do trend here, then it will show the trend coefficients. I see it takes a little bit longer maybe. Yeah, so here you can see the warming has been strongest up in the higher latitudes. Let's go back to the mean, and then we can have projection equals NP. That's the North Pole, and we can show that. So here's the North Pole projection. Or we can have sphere as well. It takes a bit longer time to get. So here's the sphere, and then you can actually get different. You can have let's see, we have ln r equals 180, so then we turn it around and run like that. Or we can also, if we have just the ordinary function here, and just show this is the original, then we can have G to DL, so that's Greenwich to dateline, so that swaps between the different ways of starting from the Greenwich or from the dateline. We can also plot the so this is the global mean of the whole data set. The X, we see that part is not complete at the very the last year is not complete, so it goes all the way down. So we can say subsets, and then index time equals C 1948 and 2017. And then we write equals false. So now we can get a new graph showing the temperature, and we don't mess up the scale with missing values. It is also possible to estimate the UFs of this data, and if we plot the UFs, we can plot. So this is the first UF pattern here. So it shows the first one by default, which explains 42% of the variance. You can see it's going up. We can also plot IEP equals 2, that's index pattern 2, so then we have the second most important UF pattern here. Another thing that we can do is if we get a station data and then we can combine it with the gridded data. So we can regrid, use regrid to estimate a time series with the same, so IS, that's the same spatial coordinates as Oslo, so that because it's a station, it will think it's a station as well, and we can combine these together and we can show them together like this. The thing is that there's an offset, so if we can write anomaly like that, and then we can plot these again, and then we see that there's a better match. So there's an offset here, and the temperatures within Oslo vary with a couple of degrees. So when you compare it with like a 2 degree by 2 degree mean value, then of course there will be differences. But on an annual timescale, you expect them to be fairly similar. So, and you can also regrid the fields from one field to another field. So if we read another data set, retrieve, and now we have data CMIP RCP 4.5. First one here. So it takes a little while to read in. And then we have small set equals x, and then is equals small x. So then basically we'll regrid it to the region of Africa, and then we should be able to do a map to show what we get. So it's there's a lot of data, so it takes a little while to actually complete, but the regrid function is quite fast, considering that it's running on a laptop and the volume of data. And the regrid can be done also in time as well as space. So here we have the map here, the same grid as what we had for the reanalysis. So that is in a nutshell how to use fields.